As I said, we're going to cover analysis of variance, and we're going to cover contingency tables, which include odds ratio, relative risk, chi-square, and so on and so forth. Now, one of the keys here is what kind of variables that we're working with. Analysis of variance. In analysis of variance, you're doing a procedure that's very similar to the t-test, okay? Except you're evaluating whether means between different groups or different populations are the same or different using the variability within the groups and between the groups. I'm not going to go. We did that in classes. You can go back and take a look at the video from class, but so I won't go over too much of that. The analysis of variance is another way to do a t-test, but to evaluate more than two samples. A t-test, you're evaluating the mean of one group against the mean of another group. With analysis of variance, you're able to analyze the differences in means between more than two groups, three groups, or four groups, or five groups, or whatever number of groups that you want. Okay, now, why would you not just use the t-test for this? Let's say we have five groups, group A, group B, group C, group D, group E. If you use the t-test to see if there's a difference between group A and group B, well, okay, fine. You'd set your alpha at 5%, and you'd be happy if you'd be happy taking the risk of 5% chance of being wrong if you reject a null hypothesis, or make exactly the kind of error that we don't want to make, a type 1 error. Actually, you can use a t-test. I'll get Manu. Very interesting that you should bring that up. I'm going to get to it in a little while to show you the similarity between the t-test and the analysis of variance. They're really the same kind of test. In fact, you're going to see that if we use the analysis of variance with only two samples, what we would normally do with a t-test, you're going to get the same result with the analysis of variance that you would get the t-test. That's what Manu is referring to. Very good. I'm glad you brought that up. But let's hold off on that. But the reason why you might not use the t-test for multiple analyses of means is that, for instance, if you compare group A to group B, you'd have 5% chance of being wrong if you reject the null hypothesis. Then you did group A against group C, and group C against group D, and A against E, and so on and so forth. And then you went back, and we've already done A and B, so now you'd have to do B and C, and C and D, B and D, and B and E, and then you'd have to go back and do C and D. So you'd have to do it for five groups, comparing the means of five groups. You'd have to do many t-tests to do that. Not only would that be unwieldy, but it also introduces a lot of error. Each time you do it, you're rejecting null hypothesis based on 5%, less than a 5% chance of being wrong. But if you do it many, many times, you're increasing your risk. Eventually, you're going to be wrong. Okay, so we need another method for comparing all of them at once, and that's our analysis of variance. Well, let's go through this and take a look at how it differs, how it's the same and how it differs from the t-test. Yeah, becomes the alpha because you do it over and over again. It's kind of like Russian roulette. Chances of shooting yourself with a gun is 1 in 6, right? But if you do it 6 times, now all of a sudden it's a lot more than 1 in 6, isn't it? So at any rate, okay, we're going to use a data file, total cholesterol by education. We're investigating whether or not people with higher levels of education have different levels of cholesterol. Perhaps their diet's better, perhaps they get more or maybe it's worse. Perhaps they get less exercise than people that have lower levels of education. We don't know. Two-sided test here because we don't know one is going to be bigger than the other. We want to see if the level of education impacts the a person's total cholesterol. Okay, and we want to prove that there's a difference in the average total cholesterol based on the level of education. Okay, so what kind of variable is total cholesterol? Any opinions on that? Well, if we look at our data, I'm going to open that file. Let me go to SPSS. I think I opened it ahead of time, so we wouldn't have to wait. Yeah, I did. Open. Data. And I'm going to go navigate to it. Whoops. Didn't mean to do that. Open. Data. And let's navigate to it. It's on my desktop. And it's in Let's see, it's here somewhere. Let me find it. Here we go. Okay, and here is total cholesterol by education. Okay, total cholesterol is a numerical, or as SPSS calls it, a scalar variable. They mean the same thing. Okay, it's total. You can see total cholesterol is a number. Okay, and I'm going to go into the variable view, and you can see total cholesterol is is the variable number 2, and the variable name is T cholesterol. The label, I'm gonna change this a little bit because we're going to want other people to be able to read this. So I'm going to click in here. I'm going to type in total cholesterol. So now total cholesterol will actually show up in the charts and tables rather than T cholesterol. Okay, and it's a scalar variable, so that's all set up correctly. Okay, well, how about education? Let's take a look at what kind of variable education is. What is it? Well, education is defined as 1, 2, 1, 3. I see some 2's in there also. The level of education is defined as 1, 2, and 3. However, that 1, 2, and 3 stands for something. I'm hoping it's coded already. Yeah, in fact, it is coded. And it's coded. 1 represents graduate school, graduated high school. 2 represents some college. 3 represents graduated college. Okay, so what kind of variable would that be? Okay, and I'm going to also put this in here, level of education. Okay, and any opinions on that? What kind of variable would level of education be? Right, categorical, it's names. You could almost kind of look at it as an ordinal variable, but for our purposes, it's just separating 3 groups. Okay, so we're going to call that a nominal, as SPSS calls it, or categorical, as the textbook calls it. Okay, and it's already coded. So if I go in here to my view and I click on value labels, it'll actually show me what these values mean for each individual. And each line here represents a person that was surveyed and whose blood was tested for cholesterol. Okay, so let's go back to our, minimize this and we'll go back to our assignment. Okay, so total cholesterol is numerical or scalar. Level of education is nominal or categorical, either one would do. Okay, now we opened it, we examined the data. Let's come up with a null hypothesis. Okay, what would our null hypothesis be? Okay, we have 3 groups. We're comparing the mean cholesterol for each of the 3 groups. So what would our null hypothesis be? Good, excellent. Okay, I'm gonna use mu1, level of education 1 equals mu level of education 2 equals mu level of education 3. I use mu because we're not concerned about the sample. We're really comparing the populations. We don't know the population, so we're forced to use the samples. But in our null hypothesis, we always refer to the population means. Okay, and what's our alternative hypothesis? That's our null hypothesis. What's our alternative hypothesis? Sometimes it's easier to put this in words than it is to actually type it in. But our alternative hypothesis is that none of the means are different. Right? Wouldn't be you might put mu1 does not equal mu2 does not equal mu3, but for an analysis of variance, we don't have to have all of the means to be different. We only need 2 of them to be different. So I'm just saying none of the means are different. Okay, so okay, well, the means of at least 2 of them analysis variance. At least 2 of these means are different. Okay, excuse me. Alternative hypothesis is you're right. At least 2 of the means are different. A null hypothesis is, in words, our null hypothesis were none of the means. Okay, so we need at least 2 of them to be different to reject our null hypothesis. Okay, so let's perform an analysis of variance using SPSS. We saw in class that we could actually do this by hand if we wanted to. In fact, there's a video posted that you can go to and take a look at. That's in one of the announcements where I have 3 videos. One of them is kind of a description of analysis of variance. The second is a demonstration of it using Excel. And the third one is a demonstration of it using SPSS. Okay, so we're going to go ahead and we're going to perform analysis of variance using SPSS. So let me go back to SPSS. Okay, so where we're going to, of course, as we always do analysis, we only go to the analysis tabs. Well, now we're comparing means. We're comparing more than two means, but we're still comparing means. So I'm going down to compare means, and my choices are one sample t-test. Obviously, this is not that. Independent sample t-test is what we would do normally for a two sample t-test. Paired sample t-test is what we would do if we had two people that would, if we had each person in the test was represented two tests, like in other words, a before and after for each person. Okay, and finally we get to one-way analysis of variance. Don't worry about what one-way means right now. Okay, in the dependence list, we're going to put our numerical variable, and our numerical variable is, of course, is total cholesterol. If you forget that, this is not really that obvious, but if you forget that, when you go down here to factor, factor or group means to break up the data into groups, factor it into groups so you can compare to different groups. And then, of course, if you're going to factor it into groups, you're factoring it into three groups, which are levels of education. So it's a little bit more obvious what this variable would be than maybe perhaps what this one would be, at least at first glance anyway. Okay, so I'm going to go ahead and do this analysis. You'll notice that there's a button here called post hoc. I'm not going to run any post hoc tests unless, whoops, I didn't have record again. There we go, it is recording now. Okay, it's recording again now. I was recording, it is recording again now. Okay, so at any rate, I'm going to go ahead now, and I'm not going to do post hoc tests unless I can reject my initial null hypothesis that there's at least two of these means that are different. So I'm going to go ahead and say, okay, there's a reason for that. Some of these post hoc tests you may get an inaccurate analysis if you assume that you can reject the null hypothesis for analysis of variance. So you don't want to do the post hoc test until you're sure that you have a significant result for analysis of variance. Okay, so now let's take a look at this. It was recording before. I turned it off briefly and turned it back on, so we're okay. So now let's take a look at this. If you guys recall, we calculated the sum of squares between the groups, okay, which is the sum of squares between each of the three means. Okay, so it was three groups, which meant there were 2 degrees of freedom. Then we calculated the sum of the squares, different squares of the differences between the groups, and because there were 135 subjects, and there were three groups, it was 135 minus 2, or 133. So our degrees of freedom was 133. So to find what's called the mean squares, in other words, kind of like the variance, we're going to take the sum of squares and divide it by the degrees of freedom. So this divided by 2 gives us 7,500. This sum of squares within the groups divided by 133 gives us 1,317. That's where these numbers come from. Now, further, if I calculate my F statistic, I get that by dividing the variability, the mean squares of differences between the groups, by the mean squares of differences within the groups. We want this to be a small number and this to be a big number. If this is a big number and this is a small number, and this is the top of the fraction, this is the bottom of the fraction, well, this getting smaller or this getting bigger will give us a bigger result, a bigger F statistic, or analysis of variance. In this case, the analysis of variance is 5.749. Now, if we did it by hand, and we analyzed this, and we found that the analysis of variance gave us a statistic of value of 5.749, we would now go to a table to determine whether we can reject the null hypothesis. Well, there's 2 degrees of freedom, Lucia. There's 2 degrees of freedom. 1 degree of freedom is for the analysis of the sum of squares between the groups. That's actually the sum of that's the sum of squares between the three means. There's three groups, so there's three means, and this is the sum of squares, the difference between each mean for each group and the mean for all of the groups. That's what this number is, squared and so on and so forth. That's what this number is. And the degrees of freedom are the number of groups minus 1. So that's 3 minus 1 is 2. Now this is within the groups. Okay, there again, there are three groups. So there are 136 people, right? So there's 135 people. And there are 133 minus, I'm sorry, I think it's 136 people. So it's 133 minus the number of groups, which is 133. 136 minus 133. Let's check that as a matter of fact, just to make sure I got that right. There is, yeah, indeed, there is 136 people, right? So it's 136 minus 3 for 1 for each group, okay? And that's the number of people minus the number of groups, okay? That's where they came from, okay? And this divided into the sum of squares between the groups, 2 divided into some gives us a 7,000. 133 divided into sum of squares within the groups is 13, and 7,500 divided by 1,300 gives us the 5.79. So now, if I were to go to my table for analysis of variance and determine the critical value for the F statistic for the analysis of variance, I would find that, let's see if I can't find that, reference tables. Let me just alphabetize these. Here is our analysis of variance. Okay. Okay, now these are on Blackboard now. There's a tab for these on Blackboard, so you'll have them whenever you need them if you need to look them up. It says 130. Why does the total say? Total on mine, I think, said 136. Where's the total 135? I'm sorry. Let me go back there, make sure we're all right. Okay, I have 136 subjects in the table. Oh, it said 133 in the table, I believe. Let me go back to the table, the output table. So much stuff here. Let me go back to SPSS. Okay, and our output table. It says 133. Actually, they're adding the degrees of freedom together. We're not using the 135. We're only using the 133. 2 into this number, 133 into this number, and this is the total sum of squares, and that's 135. We're not using this in this particular analysis. That may have some interest for some other analysis, but for this analysis, we're just using these two lines right here. So it should come out, if you actually divide that out, you should get these same numbers. Okay, so at any rate, so if we go to our table, okay, and we go to, we have two sides to this table. The top is the degrees of freedom between the groups, which was 2, and on the side here we have the degrees of freedom within the groups, which was about 133. The closest we have is 120. It's a very large sample, this particular sample. So if I start at 2 and I go down to 120, our critical value for analysis of variance is around 3.07. Okay, if we're an infinity, it'd be 3.0, right? So it's around 3.07, maybe a little bit smaller than that even. So our critical value for, so our critical value, we don't need that. Our critical value for F is 3.07. Our calculated value is 5.7. So we've exceeded our critical value, so we can reject our null hypothesis that said that none of the means are equal to one another. None of the means are different from one another. Okay, so now SPSS has the advantage of having to be of being able to calculate the exact probability rather than just the critical value for 0.05 for an alpha of 0.05. So they did actually calculate in order to get an F score that high, that would only occur less than 1%, 0.004 or 0.4% of the time when we would be wrong rejecting the null hypothesis. That's how infrequently such an outcome would occur. Okay, so we're well below 5% or 0.05 here, so we can reject the null hypothesis. The advantage of SPSS is rather than using a critical value and just knowing whether you can reject or accept the null hypothesis, reject or fail to reject the null hypothesis, in this case, we actually know, or in many cases, we actually know the real probability of being wrong if we reject the null hypothesis. It's rarely going to be that big. Anything over 3 means you can reject the null hypothesis, but it depends on the number of degrees of freedom, like really the sample size, right? So it's unlikely to ever get that big a number for F, but clearly that would be a situation where it would be almost impossible to be wrong if you reject the null hypothesis. On the other hand, the critical value could be pretty large if you have small sample sizes. Let's bring this back up again, see if we see that happening. Oops, that's the textbook. I can't find my way back to this. Okay, let's see. Well, let's see. If you had only 2 people, 2 groups, and 2 people, right? It's enormous, right? So actually, if we had a sample size, if we had 3 groups, if we had degrees of freedom, which is 2, in other words, 3 groups, and we had only 3 people between the 2 groups, the critical value of F would be 19. And if we had four people between the 2 groups, it would be 9.55, or so on and so forth. 5 people would be 6.94. So if we had a really small sample size in the 3 groups, then we would have a t-score. We would have a f-score, which would have to be enormously high to be able to reject the null hypothesis. But that's not going to happen very often. We're not going to be working with tiny samples like that. Even as soon as you get up to even 21 people between the 3 groups, we're already down in the 3s, 3.47 and so on and so forth for 3 groups, or 3.10 for 4 groups, and so on and so forth. What was our critical value for this problem? It was, closest we got is 120 for the degrees of freedom between the groups, and the degrees of freedom, degrees of freedom within the groups was 133. So closest we have on this table is 120. And the degrees of freedom between the groups is 2. So that would bring us to a critical value of 3.07. Okay, everybody happy with that at this stage? Okay, so I want to be able to move on now and know that you guys are okay. Okay, good. All right, so let's go back to where we were. And so we can reject our null hypothesis. Well, now the problem asks you to go ahead and cut and paste these into the table. So perform an analysis, paste in the tables with the results here. So I'm going to go back to SPSS, the output. Okay, and this is our result table. I'm going to click on it. I'm going to say copy. Okay, and as I mentioned this morning, for most of you guys, you'll be able to just go here to Word. You'll be able to go up to Edit and say Paste Special, and it'll give you the opportunity to paste it in as formatted text or even as a picture. This happens to be a very small table. So if I click it in just as formatted text, it's going to fit okay. But some tables which are very large are not going to fit very well. And these tables are very hard to move or resize and so on and so forth without distorting them or without messing them up. Okay, so you'd like to be able to paste it as a picture. Unfortunately, SPSS has a problem where for some versions, particularly on a couple of Mac versions, where it doesn't allow you to, it is an SPSS problem, by the way. If you copy this, it copies it, but it doesn't copy the image version of this as it should, so that you can paste it. So what you can do with the Mac instead is that you can use a program called Graph. I have it down. I've already installed it on my bar at the bottom. You can find it by going to your Finder. I'll click on the background. We're in Finder. Go to Utilities. And in utilities, you'll find the program grab, and you can just double click it and run it from there, or you can drag it down to your menu bar so it's available all the time. It'll stick there so you don't have to keep going back to the utilities folder to get it. Okay, so what you can do there is now I'm going to go back to SPSS. What you can do there is you can go to grab. You can say, you notice the top change it, grab, file, edit, capture. Go into capture, say selection, and we can tell it we want to capture this table. And we can select the area we want to capture. It comes up with an image, and I can say, save that image to my desktop. It'll save it as a TIFF file, give it a name, and so on and so forth. Or I may not even have to bother to do that. I can just say copy, and it's now in the clipboard, so I don't need this anymore. And I can go into my Word document, and I can go ahead and get around that shortcoming or that bug in SPSS and say paste, not even paste, say paste special, just paste, and it's pasted in now as an image. Okay, and I can resize it, and I can move it around very easily, and so on and so forth, for those of you who want. Now, I mentioned this morning, for those of you guys that didn't get a chance to see it yet, I mentioned this morning if you have a very large table and it spills over the edge, for the purposes of the homework, this homework, and for the exam, I'm not going to hold you responsible for shortcomings of SPSS, not being able to paste it easily. It'll be okay, just paste it in. I don't care if it spills off of the page. Okay, I'll be able to get to the parts that I need. Okay, so at any rate, that we paste our table in. Okay, what is the value of your statistic? Value of our statistic is 5.79. I think it was 5.79. Yep, 749. Okay, what's the p-value or significance of your test? Well, it was 0.004, well below 5% or acceptable level error. We rejected a hypothesis, and we accept the alternative hypothesis. And the alternative hypothesis was that at least two of these means are different from one another, or statistically different from one another. Well, now, in order to show that which ones are statistically different from one another, we have to run a post hoc test, a test after the fact, after having confirmed that there is a difference. Okay, so we're going to go ahead and do that. I'm going to go back, and for the purposes of the homework, I said use Bonferroni. You could use any of them that you want. Okay, the ones that are most, we'll bring it up, SPSS. Okay, and I'm going to go up here to Analyze, Compare Means, One-Way Analysis of Variance. See, it's still set up the way we had it before. So if this, I'm going to click into Post Hoc. And you could use least squares, you can use Bonferroni, you can use Tukey. Those are probably the three most commonly used. Okay, for the purposes of the homework, I suggested that you use Bonferroni. They're all calculated similarly, but slightly differently. So you may get slightly different results from them. Okay, so I'm going to click Continue. And now I'm going to click OK. It's going to repeat the analysis of variance, but this time it's going to run those additional tests. Notice we have the same result here. Okay, so let's go into our post hoc test. In our post hoc test, let's see, comparing a graduated high school to some college and graduated high school to graduated college. In other words, we are comparing group 1 to group 2 and 3. Let's see what the probability of being wrong for each of those comparisons would be, if it would be less than 5%. Graduated high school versus some college, that's not a significant result. How about graduated high school versus graduated college? Well, yes, that is a significant result. It's less than 0.05. So it looks like we can reject the null hypothesis for graduated high school versus graduated college. In other words, there is a difference in the mean cholesterol between people that just graduated high school with no college and graduated college, right? So what about the rest of these? Well, some of these are repeated. This one is some college versus graduated high school. Well, we've already done that up here, and we know it's 1. This one is some college versus graduated college. Oh, well, look at that. There's a difference between them as well. So between graduated college and some college, and graduated college and graduated high school, we can show that there's a significant difference in in average total cholesterol. Okay, and in fact, you see that repeated down here. Graduated college versus these other two groups are significant. The only one that wasn't significant was comparing graduated high school to some college. Okay, so that was not a significant difference in means. So what this has allowed us to do is not just prove that there is a difference in at least two of the means, but actually identify which of the means show a statistically significant difference. Okay, and again, we would cut and paste that table into our document. Let me go back. I'm going to copy. Actually, I'm going to do it my way. I am going to grab capture selection, and I'm going to go ahead and capture that. Okay, I'm going to say copy, and then I'm not going to save this. I'll get rid of it. And I'm going to go back to my Word document. And let's see, what are your conclusions regarding hypothesis? We rejected the hypothesis. Do our post-hoc test, report our findings there. I think it's okay to just paste this in. Okay, and let's see, is there statistically difference in average cholesterol levels? Is there for men who graduated college versus men who completed high school? Well, that was yes. There is a statistically significant difference. How about between men who graduated college versus completed some college? That was a yes also. How about men who completed who had some college versus men who completed high school? No, we were not able to prove that there's a difference between those two groups. That's our analysis of variance. That's what analysis of variance is all about. Now, I don't want to ignore Manu. She brought up a really great point. Okay, so I'm going to go back here. And remember, this morning, those of you that were with us, this morning we calculated a t-score. Oh, and by the way, I had a question earlier today. Keep in mind, if you take a close look here, there are really two tests that are going on here. Look at this header over here. This header covers these two blocks over here. This header covers the rest of the analysis. So this area in here, everything under here, is just testing for the equality of the variances. Are the variances equal or different? This is the actual t-test that SPSS has run. The whole area under t-test for the equality of the means. Okay, so the significance here is only there to help us decide whether or not to assume equal variances or assume the variances are not equal. If this is less than 0.05, we go to the second line and we use that line for the t-test instead of using the top line. If this is greater than 0.05, we use the top line, which is what we wound up using in this case. I just want to point out that the significance turned out to be 0.000 and the t-test turned out to be 5.848. I am going to use the analysis of variance for this same data set, NC birth data set. I'm going to open that again. Okay, open data. And I'm going to open that data set again. And I'm going to do that comparison using the analysis of variance. Analyze descriptive statistics. Compare means. Independent samples t-test instead of analysis of analysis of variance instead of independent samples t-test, which I was using this morning for this analysis. Okay, and I'm going to say the dependence list was, again, we were comparing for married and unmarried mothers, the weight of the child at birth in ounces. That's that variable, and the factor variable was whether or not the mother was married, the marriage status of the mother. Okay, and in analysis of variance now, I'm going to go ahead and run this analysis of variance test. Now, since there were only two values for marital status, married versus unmarried, I would normally run a t-test. But let's see what happens if I run analysis of variance instead. I'm going to click OK. And, well, let's take a look at this. I wound up with the same significance that I wound up with when I ran the t-test. So you can actually use analysis of variance in this way, and you'll get the same result for the probability of being wrong if you reject the null hypothesis. when you go really back to the basics, these are really two forms of the same analysis. Okay, so just so that you know about it, if you saw that mentioned in the textbook, or if I may have previously mentioned it when we were talking about t-test and analysis variance earlier, that you can actually use it for two samples if you wanted to, and you would get the same result as using the t-test. That will indeed happen. Okay, so let's move on to chi-square. I think we're done with analysis of variance for our homework problem. What's your conclusion regarding? Oops, I stopped a little early. Okay, men who graduated college, we got that done. Okay, so now let's take a look at contingency tables. Contingency tables are similar to the crosstabs, or the tables that we were using earlier in the semester to analyze how reliable diagnostic testing was. Now, in this case, we're comparing an exposure with an outcome, an exposure, a difference, an intervention with what the outcome might be. In this case, we're talking about if any of you guys, I know I've gone to a lot of church luncheons, and whatever's made out of mayonnaise, it's summer, it's a long mass. There's a couple of meetings going on, so by the time you get to the food, it's been sitting out in the sun for quite a while, right? So those of you that attend church and go to these kind of luncheons, if it's got mayonnaise in it, stay away from it, right? So I'm sure that you might have had experience with that stuff. So following a church luncheon, many attendees are struck with acute gastric distress. You're able to interview 100 people who ate the tuna surprise. Tuna surprise, to my surprise, the first time I ever had, I was very surprised. It's basically baked tuna, tuna with mayonnaise and stuff like that. So at any rate, who ate the tuna surprise? 100 people who ate it, and 100 people did not eat it. So we want to determine, is it likely? Not everybody gets sick with some of this stuff sometimes, right? In other words, some people eat it and some people become sick. Others, maybe they'll eat it and they'll be lucky, or their immune systems or their gastrointestinal systems will tolerate a little bit better than others. So in this case, out of 100 people who ate the tuna surprise, 60 became ill. And out of 100 people who didn't eat the tuna surprise, 30, a smaller number, became ill. Okay, so now the deal here is that we want to know, well, there is a difference here, 60 versus 30. But is that difference due to chance? That it's just we happen to interview 100 people and a fewer number got sick, and we happen to come across, when we randomly select the people who ate it, that we happen to catch more of the people who became sick for that one. But there's really no difference in the rate that people got sick. Maybe it wasn't the tuna surprise. Maybe it was the peach cobbler or something like that was getting everybody sick, right? So maybe that the tuna surprise it did not give you an increased risk of getting sick. Maybe it was something else that was going on. So one of the first things we might be interested in here is, what is the risk of illness if you ate the tuna? Well, risk is simple. In fact, we're going to look at risk and odds. Risk is a little bit more intuitive. It's a little bit more the way most people think about this stuff. But as it happens, odds and biostatisticians and bookmakers for racetracks, right, tend to use odds rather than risk, right? So we're gonna go with the bookmakers and the biostatisticians most of the time in using this professionally, but many people also still use risk as well. So what's the risk of illness if you ate the tuna? Well, it's going to be 60 people out of 100 got sick that ate the tuna, so the probability of being, or the rate at which you get ill if you ate the tuna was 60%. Now, how about if you didn't eat the tuna? What's the risk there? Anybody awake out there that wants to answer that question? Right, 30%, right? 30 out of 100. Okay, and it's going to be equal to 0.30. Okay, so now, what's the relative risk? Another way of saying relative risk is called the risk ratio. Anytime you say a ratio, it means you're dividing one thing by another. So the risk ratio would be the rate at which people got sick if they ate the tuna surprise versus the rate at which they got sick if they didn't, and that's equal to 2. That's another way of saying that you're twice as likely to get sick. Very good, guys. To get sick if you ate the tuna surprise versus if you didn't. Now the question is that two, is that increased rate due to chance, just sampling error, sampling chance, or is it really indicate that eating the tuna surprise puts you at greater risk for getting sick? Well, we're gonna take a quick look at that in a moment. Okay, but let's get to this odds stuff. The way you calculate the odds is a little bit different. We calculate the odds as say 60 to 40. 60 out of 100 people, 60 got sick, 40 didn't get sick. So the odds of getting sick versus not getting sick are 60 to 40. Okay, or what's that going to be? That's going to be equal to 1.5. Okay, and what are the odds of getting sick if you didn't eat the tuna surprise? Well, it's 30 to 70. Okay, and that's equal to let's use our calculator. Okay, that's 0.4. I'm going to call it 0.43. I'm going to round it off to 0.43 or 0.4. I'll use 0.42. Why not? Okay, 0.42, as Katie suggested. So now what's the odds ratio? Well, the odds ratio, again, the ratio is just a ratio between two numbers. It's a fraction. Is 1.5 divided by 0.42. Okay, 3.5. I'll take you guys' your word for it. 3.5, save a little time. Okay, so the odds are 3.5 times greater to get sick if you ate the tuna surprise, and the risk was twice as great. Two ways of saying the same thing. We get a somewhat different number, but they're really kind of giving us a picture of the increased risk or the increased rate at which the exposure can make you ill. Okay, so now the thing is, just like with the risk, we need to know whether that 3.5 is that due to chance or is that due to an actual difference in the odds of getting sick if you ate the tuna surprise. And the real way that we determine that is we have to calculate a confidence interval for the relative risk. And if the confidence interval is say 1.5 to 2.5, that would indicate we're 95% certain that the true relative risk for this population is between 1.5 and 2.5. We're 95% certain. And since two is inside, excuse me, if there's no difference in risk, the rate would be the same for both of them, right? If there's no difference in risk, we would expect the relative risk to be equal to 1, right? So since we know that we're 95% sure the true relative risk is between 1.5 and 2.5, we know with 95% certainty that it's different than 1. It's almost like doing a single sample t-test in a way, right? But not really a t-test. So since it excludes 1, we can reject the null hypothesis that there's no association between tuna surprise and getting sick. Okay, that would be our null hypothesis. Okay, we're going to get to that in a second, I think. Okay, same deal with the confidence with the odds ratio. The odds ratio, if there's no difference in risk, the odds ratio would be equal to 1. You have to make sure the 95% confidence interval for the odds ratio that you calculate is different than 1. Now, we could do this by hand, but in our case, we're going to be happy to do it using SPSS. So now I'm going to skip this for a moment, and I'm going to go on to this table because I want to illustrate for you the fact that there's another way we can look at this as well. And we can look at this from the perspective of, well, this is what it looked like when we actually asked people if they got sick and what they ate. This is our observed values. Okay. Well, I'm going to take another look at this. I'm going to look at it a different way, and that would be if there was no difference in the rate at which people that ate the tuna surprise got sick, and the rate at which they didn't eat it got sick, then I would have a table just like this, except my expected values might be different than the ones that I observed. Well, let's decide what our expected values should look like. I copied everything in this table except for the four numbers that are in the center of the table. Now, notice that out of the 200 people, 90 people got ill, 110 people didn't get ill. So 45%, 90 over 200, was the percentage of people, whether they ate the tuna fish surprise or didn't. That's the percentage. That's the rate at which they got sick. So I'm going to go down here, and I'm going to remind you that the rate at which people got sick, the rate at which rate for the entire group, entire population, is 90 over 200. Okay, in other words, 45% of the people got sick, whether they ate the tuna surprise or not. Well, if that's true, if that's true, and if it's true that there's no difference between eating it and not eating it, if we took 100 people that ate it, we would expect 45 or 45% of those 100 people to get sick. And if there was no difference in skipping it or eating it, we would also expect 45%. In other words, if it was the peach cobbler instead. Kind of like the prevalence, exactly right. It's basically the prevalence. And we're getting the prevalence from this table, from our observed values. We're using this total number of people that got sick and the total number of people sampled. We're using that to get our prevalence, really. Yes. So I can fill in all these values now, right? This would be 55 and 55. Okay, now I put this table together so it would come out whole numbers. It would not be unusual for the expected values, to come out as fractional numbers. Because let's say it had been 47 and a half, the prevalence had been 47 and a half, right? Let's say it had been 91 out of 200 and 200. 91 out of 200 would have been 0.455. So this would have been 45.5 and 45.5 and 54.5. So you could get fractional values there as well. Okay, so we're going to do an analysis which compares the values that we observed versus the expected values that we would have expected to see if there was no difference. Okay, so let's state our null and alternative hypothesis. Well, this is one of the places where it's a little easier to state it as a word, and that is there is no association between tuna surprise and cramps. Okay, and the H alternative is that there is an association. You're more likely to get it if you get cramps if you ate that tuna surprise. Okay, so perform a chi-square analysis, and the way we calculate this is that I'm going to go ahead and take. Now, I'm not going to go through the whole analysis right now to save some time. You remember in class the way that we did this was we took the value here, 60. We found the difference between the observed value in that cell and the expected value, so that would be 15. We squared, the difference would be 15. Observed minus expected would be 15. We squared that, which would be 225, and we divided it by the observed values, which is the observed value, which was 14. So just for that one box, it would be, whoops, where'd it go? There it is, back here. It's hidden back here. Okay, so 225 divided by 45 is equal to 5. So the value we would have gotten for that would have been 5. Now I repeat it with the next box. 40 minus 55 would be 15 squared would be 225 divided by 55 would give us another number, and a third number, and a fourth number. And we would add those four numbers together. And then we would take that total, and that would be our chi-square value. Now, I've already gotten a couple of questions. the chi-square tends to overestimate the chances of give you too good a chance to reject the null hypothesis in a 2 by 2 table. There's certain issues with 2 by 2 tables that will make it more likely that you will incorrectly reject the null hypothesis than the chi-square table would suggest. Okay, so what many people do with a 2 by 2 table is they do something called a Yates or continuity correction. And what they do is they take the difference, 60 minus 45, and they also subtract 1/2 from that, right? So instead of being 15, it's 14.5. They square the 14.5 and then put that over 45. So it makes it a slightly smaller number. It makes it a more conservative estimate of the chi-square value. For our purposes, if you do it in the future, real life, you will use the continuity correction mostly if you're going to actually publish the information. But for our purposes, rather than complicate the calculation, I'm going to say that we don't need to use it for our purposes. Okay, so that's really what that Yates or continuity correction is all about. So I am going to ignore that for the moment. Okay, and I'm going to go down here and I'm going to say how many degrees of freedom. Okay, well, let's see. How many degrees of freedom does our analysis involve? Anybody remember how you calculate degrees of freedom for chi-square analysis? It is right. It's the rows minus 1 times column minus 1. So in this case, it's equal to 1. Number of rows minus 1 times number of columns minus 1. In this case, it's equal to 1. So you could have 8 tuna surprise, skip the tuna surprise, 8 the peach cobbler, 8 this other stuff. You could actually have more rows or more columns for different outcomes, more exposures or more outcomes, and you could have a 2 by 3 table, a 2 by 4 table, a 3 by 5 table, you name it. You could still do these kind of analyses. Okay, so how many degrees of freedom do we have? We have 1. What's the critical value for a situation where we have 1 degree of freedom for the chi-square value? Okay, so now we're going to go back to our reference tables. Okay, we're going to look at chi-square. Where to go? I have it here somewhere. That's the Z table, T table. I thought I had it here. I guess I don't. You know, I think we've been going on the web and I just never bothered to save it. Yeah. Okay. Actually, let me see. I have the textbook open here. Let's look at the tables. I think we have a bunch of tables at the back here. Let's see. Chi-square table 274. What page is this? I think there was one back there too, but it said 274, so I'll go to 274. Oh, got to go a lot further back than that. Doesn't have a value for 1? Oh, you're right. I don't know why that's the case. You're absolutely right. I remember that came up, didn't it? That they don't have a value for 1. I don't know. Okay. Chi-square table. Okay, let's see if we can find one. That'll give us what we need. Nope, that's not what we need. Yeah, I guess we do. I guess we have this. Okay, so 95% in confidence or 0.05 chance, 5% chance of being wrong. Okay, so our chi-square value, oops, no, this is the wrong. This is degrees of freedom, 1 area to the right of the critical value. Actually, this is a funky table. This actually does have the value. The area to the right of the critical value, 5%. That's the level of confidence that we want. That's we want our alpha is 5%. For 1 degree of freedom, our chi-square value has to exceed the critical value of 3.84. I'll find you a better table than that. That's a little less confusing. I know we saw a couple here, but that's one of the ways that you might use that particular table. Now it's laid out the same way. So anyway, the chi-square value is 3.84. Yeah, I'll put a good one into the reference table when I get a chance to. I don't want to kill too much more time on this. When I get a chance to look one up, I'll find a good one for you. Okay, so what's the critical value? What's critical value for chi-square? For 1 degree of freedom, it's 3.84. Does your calculated chi-square value exceed the critical value? Well, you want to know something. We only did one cell, and that one cell came out to be 5. And that's all we needed. We know that it exceeded that when we added the other numbers, it'd be even greater than 5. So yes, we exceeded the critical value, even though I didn't calculate the rest of them. So what are your conclusions? Well, we reject the null hypothesis, right? And then that there is no association between that nasty tuna surprise and cramps. Okay, and we accept the alternative hypothesis, right? That there is an association. Okay, I'm going to repeat this analysis right now using SPSS. Okay, as it happens, I created a file, open data. Stay away from the tuna surprise at church picnics.save. It's always it says two-sided. It's really a one-sided test. There is no, you're only testing the right side, but that's the only part that's important in this test. So SPSS calls it a two-sided test. I presume that's to avoid confusing and avoid getting someone to double the p-value that it produces, thinking that it would be appropriate to do that for a two-sided test. Okay, so let's do this analysis. Analyze. We're not comparing means. Let's go into descriptive statistics. Well, we have a table thing called here crosstabs. In other words, building tables like this, rows and columns. So I'll click that. And in fact, it allows us to create tables in rows and columns. We put the exposure into the rows and the outcome into the columns. So the exposure was eating tuna surprise. The outcome is whether or not you got ill. Okay, so I'm going to go into statistics. I'm not going to mess around like we did in class. I'm going to go right to the bottom of this, and I'm going to click chi-square. We want to calculate the chi-square, and I'm going to click risk. We want to calculate the risk as well, and I'll click continue. I'm going to click under cells. It's going to print out observed values. You could also get it to click out the expected values, percentage by rows, and so on and so forth. For our purposes, I'm just going to get it to print out. If I get it, well, why not? Let's do them all. And I'm going to go ahead and do the calculation. Okay, so what do we get? Let's take a look. First thing it tells us is that there were 200 people in this study, right? And everybody, we have responses for everybody. There's no missing values. Then we go down here and we see our crosstab table. Here are our expected values. Here's our exposure, tuna surprise, ate it, didn't eat it, and our columns became ill, did not become ill. And what are the counts? What is our observed values or counts? 60 and 40, 30 and 70, as we expected. Our overall rate of getting ill was 45%. What are our expected values? 45, as we did before, and 45 here, because the sample sizes are the same, 55 and 55. Right, so they summarized it in a single table, but they got the same results as we did. Okay, so now I'm going to go down to this other table where it actually performs the actual tests. Okay, well, Pearson's chi-square, if we had actually gone through all those boxes and calculated chi-square value, we would have discovered that our value would have been 18.182. We know the critical value for 1 degree of freedom was 3.84, so So we know we could reject it. In fact, the probability of being wrong if we reject the null hypothesis using the technique we just used, Pearson's chi-square, is less than 1/10 of 1%, 0.000. Okay, if we had used the continuity correction, we would have gotten a slightly smaller value for chi-square, but we still have a very significant result. So we would reject it in either case. Okay, in this case, we would have subtracted 1/2 from the top before we squared it. Okay, so that's our chi-square and our probabilities, and we can reject the null hypothesis. Let's take a look at our risk. Our odds ratio that we calculated manually, well, that was 3.5. And it doesn't really call it our relative risk, but the next box is relative risk, was 2.0, just the way we calculated ourselves. SPSS, on the other hand, because it worked out this probability, it's basically a binomial probability, it worked out the probability and calculated the 95% confidence interval for us. So based on our results, it looks like between our people that were exposed and our people who weren't exposed, it looks like the odds are 3.5 times as great for people that ate the tuna salad to become ill. In fact, we're not really sure it's 3.5, but we are 95% certain that the true increase in odds for eating the tuna salad, the tuna surprise, is 1.9 to 6.2. Since this excludes 1, since we know with 95% certainty that the odds ratio is different than 1, we can say that the tuna surprise, reject the null hypothesis that the tuna surprise is not associated with getting sick, and accept the alternative that it is associated. And we can see the same thing for the relative risk here. It's 2.0 with a confidence interval of 1.4 to 2.8, so it excludes 1, so we can reject the null hypothesis here as well. So I can copy and paste these tables just as I did before into our Word document and answer that question. I think that's it. Confidence interval. Based on its confidence, can you reject your null hypothesis? And the answer was yes. You can.